Imagine this for a moment. The next time you ask AI a question, the answer may not come from a building on Earth, but from a data center floating quietly in space, powered entirely by the sun. Sounds like a science fiction? Today's article tells us that it may soon be a science fact. I'm Dr. Nisha Jacob from Career Guidance and Adolescent Counseling Cell, Alapura. Let's explore a fascinating article titled, Can Data Centers in Orbit Solve for AI Models Energy Demand? This article is written by Sri Aaron D. He is a technology and science journalist known for explaining complex technological developments in a way that connects them to society, economics, and policy. The article begins with a powerful reality. Data centers are consuming a growing share of the world's electricity because artificial intelligence depends on massive clusters of GPUs, continuous computation, training and deploying large language models. As generative AI grows very rapidly, databases are consuming more energy than ever using whatever electricity sources are available. This raises a critical question. Where will the energy for the future AI come from? To address this problem, Google Research is exploring a bold idea, launching data centers into space and powering them entirely with solar energy. This project is called Project Suncatcher. Even ISRO is reportedly studying space-based data center technology, showing that this is not a fringe idea anymore. Project Suncatcher proposes data center placed in low Earth orbit, powered continuously by the sun, organized as dense satellite clusters similar to Starlink. Unlike Earth-based solar plants, these data centers would always remain in sunlight, avoid weather interruptions, and receive constant solar energy. The satellites would follow carefully choreographed orbits, always maintaining the line of sight with the sun. The article explains something counterintuitive. For AI data centers, internal bandwidth matters more than internet speed. AI systems require fast data exchange within the data center itself. Most of the data traffic stays inside the system, not between users and servers. An analogy used: just like ChatGPT needs massive internal connections, users only need modest bandwidth to send queries and receive responses. Thus, downlink speed to Earth is less critical. In space, workloads could be distributed across multiple satellites. Satellites would share data using high bandwidth radio beams. New multiplexing technologies allow more data per signal. This makes it possible for space-based data centers to operate efficiently, remain functional with enough power, and avoid the need for massive Earth-based connectivity. Space is not friendly. One major challenge is solar radiation. The article notes, high bandwidth memory is especially sensitive. Damage appears only after cumulative radiation exposure. However, Google research found their Trillium TPUs survived radiation doses much higher than expected. No hard failures occurred even near tested limits. This suggests that modern AI chips may be more space ready than assumed. Here lies a serious issue: heat management in space. On Earth, data centers use liquid cooling. In space, there is no air and heat must be dissipated in a vacuum. A space data center is constantly blasted by solar energy, required to release heat efficiently. This means one of the hardest engineering challenges. The article emphasizes economics may be the biggest obstacle. For space data centers to work, launch costs must drop definitely, maintenance and replacement must be affordable, and total cost must compete with ground-based data centers. Google estimates that satellite launch costs may fall to $200 per kilogram by the mid-2030s. Combined with power savings, this could make the idea viable. But success depends on multiple technologies advancing together. The article reminds us many once doubted technologies like Starlink eventually succeeded. But others like Microsoft's underwater data center project Natick were abandoned. This skepticism is reasonable, but dismissal may be premature. It opens doors to future careers in AI, space technology, energy systems, and sustainability. It explains why AI affects electricity costs, climate concerns, and global infrastructure choices. It highlights the need to balance innovation, economics, energy security, and environmental responsibility. This article reminds us that the future of AI may not just be smarter, it may also be higher, cleaner, and orbiting above us. I'm Dr. Nisha Jacob from Career Guidance and Adolescent Counseling Cell, Alapura. Thank you for listening and keep looking up because the future of technology may truly be in orbit.